packing efficiency of different types of unit cell. We will start with the first one, that is HCP or CCP. Both have same type of packing efficiencies. So the first case is HCP, which is hexagonal close packing, or cubic close packing, CCP. Now if we draw the unit cell for HCP or CCP, it is somewhat like this. Where the atoms, molecules, or in short the constituent particles are present at all the corners, and along with it each of the atoms or molecules is present at the center of each face. Now if we want to draw the number of spheres at each corner and center of each face, let us take only one face at a time, and suppose this is the first sphere present at a corner. There is another sphere which is present at the center of this face, and another sphere which is present at the corner of this face. Correct? Although there are spheres at each corner of this cube and at each face, center of each face, we are considering only one face just for the sake of calculation of packing efficiency. Now suppose if I say the edge length of this cube is represented by small a, then the angles between any two edges is actually 90 degrees. So if I take this face, the angle between, suppose if I name this cube as say A, B, this corner as C, D, this corner as E, F, G, H. Suppose I have named all the corners as A, B, C, D, E, F, G, H respectively, then the angle between the edge length CD and ED is 90 degrees. So if I draw this diagonal, if I connect the points E and C, which will be the diagonal of this face BCED, we are considering only face BCED just for the sake of calculation of packing efficiency of HCP or CCP. Now the angle between the edge length CD and ED is 90 degrees. The angle between any two edge lengths is actually 90 degrees. If we consider the face BCDE, then the angle between the edge length CD and ED is also 90 degrees. So if I connect this diagonal from E to C, then this triangle EDC is actually a right angle triangle. This triangle, which is E, D and C, this triangle EDC is a right angle triangle and right angle at D, 90 degrees at D, and the spheres are present at this corner E, at the center of this diagonal EC, and also at this corner C. Correct? Now if the edge lengths are represented by small a, which means ED is also small a and DC is also small a, and the radius of each sphere, each identical sphere is small r, then this length is 2r, this length is r, and this length is r. It means the diagonal length EC is nothing but r plus 2r plus r, that is 4r. Now if we apply Pythagoras theorem in this right angle triangle EDC, then we can say that EC square, which is the hypotenuse of this triangle, EC is the diagonal and also the hypotenuse of this triangle, is equal to ED square plus DC square. Correct? The hypotenuse, the square of the hypotenuse is equal to the sum of the square of the rest of the two sides of this right angle triangle. Now we can write that 4r square. Why? Because the length of EC is nothing but R plus 2R plus R, correct, is equal to A square plus A square. Why? Because ED is also A, the edge length of this, all the edge lengths are same because these edge lengths represents the sides of a cube, and in cube all the side lengths are equal. So if I represent any of the side as small a, it means all of the sides are equal in length, that is small a. So ED is also small a and DC is also small a. So A square plus A square is equal to the length of EC, square of the length of EC, and the length of EC is nothing but R plus 2R plus R, that is 4R. So it becomes square of 4R, correct. Now if I try to solve this, it becomes 16R square is equal to 2A square, correct, or in short it will become 8R square is equal to A square. How? If I bring 2 below the 16, then 2 into 8 is 16, so the 16 will get cancelled and it will become 8. So A square is equal to 8R square. If I root this equation, it will become A is equal to root 8 into R. I can bring out R outside this root because it is square, and 8 will be inside the root, it will become root 8. Or in other words, A is equal to 2 root 2 R. Why? Because root 8 is nothing but root of 2 square into 2, square of 2, that 2 comes out, so it becomes 2 root 2. So A is equal to 2 root 2 R. Okay. Now this is the relation between the edge length A of this cube of this unit cell and the radius of sphere, that is small r. Okay. Now if we talk about packing efficiency, we'll use some notations. We'll represent packing efficiency as P dot E, which means packing efficiency. Now packing efficiency is actually occupied volume by spheres upon total volume of unit cell into 100. Correct? So packing efficiency basically means what is the volume occupied by the constituent particles in this cube, which is spheres. So what is the occupied volume of spheres inside this cube upon total volume of this cube, that is total volume of the unit cell, into 100, that is packing efficiency. Now we'll represent this occupied volume as OC and total volume as TB. So it becomes, this packing efficiency becomes PE is equal to OC, that is occupied volume, upon total volume into 100. Just for the sake of convenience, we'll represent occupied volume of spheres as OC. OC means occupied volume, and total volume of unit cell is TB. Correct. Now if I substitute occupied volume and total volume in this relation, and if I calculate that, I can get packing efficiency. Now what is the occupied volume? Now as we know, in HCP or CCP, that is almost like face-centered cubic unit cell, has 4 atoms in it or 4 spheres in it. Effective number of spheres in this type of unit cell is 4. Now the volume of one sphere is 4 by 3 pi r cube. I am sure you have heard about that in mensuration in lower standards. Volume of a sphere is 4 by 3 pi r cube. Now since there are 4 spheres inside this particular cube, HCP or CCP, the total occupied volume will be nothing but, it will be 4 into 4 by 3 pi r cube upon. Now since the edge length of this cube is represented by small a, and the volume of a cube is length into breadth into height, since length is equal to breadth is equal to height of a cube, so it means a into a into a, which means a cube. So the volume of this cube becomes a cube into 100. Correct? Now since we have two variables, r in the numerator and a in the denominator, it is very important to have a relation between A and R, so that the variables get cancelled and we are left with numbers only. And that is how we can calculate the packing efficiency. And this is why we have done this work on the right hand side, that is we have used the Pythagoras theorem, correct, to find the relation between A and R by choosing one of the face of this particular cube and applying Pythagoras theorem to one of the triangle formed if I join the diagonal EC. Doesn't matter if you have used diagonal BD also, then also you will get the same relation. If you use any of the face in fact from the cube, you will get the same relation between A and R. This is just for the sake of convenience in our calculation, that we have used the face BC, DE and the diagonal EC and the triangle EDC, that is right angle triangle, right angle at D. Correct? So we have a relation between A and R. If I substitute A as 2 root 2 R over here, this becomes 4 into 4 by 3 pi R cube upon 2 root 2 R cube into 100. Correct? Now if I open this bracket in the denominator, everything will become cube, cube of 2, cube of root 2 and cube of R. We have already a cube of R in the numerator, we will now have in the denominator also. So it will get cancelled. How? Let us see. So it will become 4 into 4 by 3 pi upon cube of 2 is 8, cube of root 2 is 2 root 2. In the numerator also we have R cube, in the denominator also now we have R cube into 100. So this R cube gets cancelled. Okay? Now let me solve this, let me carry out this operation over here. So this packing efficiency becomes, if I calculate this packing efficiency here, this packing efficiency now becomes, you can see this 4 into 4 by 3 pi is left in the numerator and 8 into 2 root 2 is left in the denominator. So it becomes 4 into 4 by 3 pi upon 8 into 2 root 2 into 100, and R cube gets cancelled in present in numerator and denominator. So if I try to solve this, 2 2s are 4, 4 into 2 8, so 4 into 2 8 gets cancelled with this 8 present in the denominator. So it becomes pi upon 3 root 2 into 100. Now if I solve this numbers, if I substitute the value of pi as 3.14 or 22 by 7 divided by 3 root 2 into 100, if I solve this packing efficiency turn out to be almost 74%. 74%. If you substitute the value of pi as 3.14 over there in the numerator, divided by 3 root 2, the value of root 2 is 1.414, and if you multiply the result, that fraction into 100 by 100, then packing efficiency turns out to be almost 74%. Now remember, both HCP and CCP have equal packing efficiencies, that is coming out to be 74%. Also this is face-centered cubic unit cell, where spheres are not only present at the corners of the cube but also at the center of each face. Just for the sake of convenience of calculation, we have considered only one face, that is BCDE. We have joined only one diagonal, that is EC of that face, and we have considered only one triangle of that face, that is triangle CDE, which is right angle and right angle at D. We have applied Pythagoras theorem in this triangle EDC. Why? To generate a relation between the edge length A of this cube and radius of these identical spheres R. So by doing so, we have generated the relation as A is equal to 2 root 2 R. Now packing efficiency always means the total occupied volume of spheres divided by total volume of unit cell into 100. This fraction into 100. Now occupied volume of spheres means the total number of spheres you have in this unit cell, you multiply with the volume of each sphere, you will get the total occupied volume of the spheres. Now, as I said earlier also, you might have studied in lower standard in mensuration that the volume of a sphere is 4 by 3 pi r cube, and since there are effectively four spheres in this unit cell, so a total occupied volume, or in short occupied volume of spheres, becomes simply 4 into 4 by 3 pi r cube. And since the denominator is total volume of unit cell, since this unit cell is in the form of a cube whose edge length is represented by small a, therefore the volume of this cube becomes a cube. Now, since we have two types of variables in numerator and denominator, that is r and a, we need to have a relation between a and r, which is coming out to be a is equal to 2 root 2 r. So if I substitute 2 root 2 r in place of a, the denominator becomes the cube of 2 root 2 r, and if I open this bracket and cube each of the numbers and variable written in this bracket in the denominator, it will become cube of 2, that is a, into cube of root 2, that is root 2 into root 2 into root 2, 3 times. So root 2 into root 2 becomes 2, into root 2 becomes 2 root 2. So, and cube of r becomes r cube. So denominator becomes 8 into 2 root 2 into r cube. Now you have r cube in the numerator also, you have r cube in the denominator also. So that both the r cube gets cancelled, you are left with numbers only. Now since we are left with numbers only, it is very easy to calculate the packing efficiency, and if we solve these numbers by substituting the value of pi is equal to 3.14 and root 2 as 1.414 as the value of root 2 is 1.414, this packing efficiency comes out to be almost 74%. Calculate the packing efficiency of body-centered cubic unit cell or body-centered cubic unit structures. Okay. Now if you remember, in body-centered cubic unit cell, you have spheres present at all the corners along with a sphere present at the center of the body. Correct? And the number of atoms or number of spheres turning out to be in such type of cell was 2. So let us draw the structure first. Suppose this is the unit cell, correct, in shape of a cube, right? Now since we have atoms or spheres present at all the corners along with a constituent sphere or a constituent atom present at the center of the body, let us choose the body diagonal and two opposite corners of this cube for the sake of convenience of calculation of packing efficiency of BCC. Suppose if I mark these corners as A, B, C, D, E, F, G and H. These are the names of the corners of this cubic unit cell. Correct? Now, since we have atoms present at each corner, so I have chosen two opposite corners, that is A and D. A is a corner of face A, B, E, H, whereas D is a corner of opposite face. Try and understand, there are two different phases, opposite phases. I have chosen A of this face, A corner of this face, and D corner of the opposite face, so that if I join AD, it becomes a body diagonal. Also, there is an atom present at the center of this body. Correct? Now, if I try to join this AD, it becomes the body diagonal. Now, try and understand. Suppose if I say, let us consider triangle GHD. The top face has HD as diagonal. The top face has HD as diagonal. So if I consider triangle HGD, if I consider the triangle HGD, basically right angle triangle HGD, where the angle G or HGD, the angle HGD is 90 degrees. Now HG is edge length, GD is also edge length of this cube, and let us assume that the edge length is represented by small a. Then on the top face HGDE, we have considered the right angle triangle HGD, where the two sides other than hypotenuse is A and A, small a and small a. Why? Because they are the edge lengths of this cube. And HD is the hypotenuse of this particular right triangle. So if I apply Pythagoras theorem in this triangle, then the square of the hypotenuse, that is HD square, is equal to HG square plus GD square. Correct? Now if I substitute HG as small a, which is the edge length, and GD as also as small a, which is the edge length, then this becomes a square plus a square, which is equal to 2a square. HD square is equal to 2a square. And if I root this equation, then HD becomes simply root 2a. Correct? So finally I have the diagonal of this face, the top face HD, as root 2a. Now if you see this triangle AHD, then the angle AHD is also 90 degrees. Why? Because they are perpendicular planes. The top plane, the top face, has face diagonal, correct? And from the same point H, there goes a vertical line below this plane. So the angle between this line and this diagonal should be 90 degrees. And since this diagonal, face diagonal HD, and this edge length HA have 90 degrees, it means the body diagonal AD becomes hypotenuse of this triangle. So if I choose, once again, if I choose, say, right angle triangle AHD, the right angle triangle AHD, right angled at edge, which means the angle AHD is 90 degrees, then the hypotenuse becomes AD. So I can write AD square is equal to the sum of the squares of the rest two sides of this right angle triangle, which is AH square and plus HD square. AH square plus HD square. Now AH represents one of the edge length of this cube, and since we have edge length represented by small a and all the edge lengths are equal as it is a cube, then AH is also small a. So in place of AH I can write small a or square of small a. Now HD is face diagonal of this top face, correct? It's the face diagonal and it was coming out to be root 2a. Now since we have square of HD, it will become square of root 2a. Now if I open this bracket, root 2a square, if I open this bracket, then square of root 2 becomes root 2 into root 2, that is 2, and a square. So it becomes a square plus 2a square. Now a square plus 2a square means 3a square. So finally the body diagonal AD square, one of the body diagonals rather I should say, one of the body diagonals AD square is 3a square. If I root this equation, then AD becomes simply root 3a. A will come out of the root because it is square and 3 will be inside the root. So the body diagonal AD is now root 3a. Now if you see this body diagonal root 3a, it is actually R of this corner, sphere of this corner, at this corner, 2R of the atom or sphere at the center of the body, plus R at this corner of the cube. So basically this body diagonal is nothing but sum of small r plus 2r plus r, which is r plus 2r plus r, that is 4r. So this body diagonal, we can say this body diagonal AD is also equal to 4r. The sum of radius of this sphere present at this corner and the diameter of this central sphere, the sphere present at the body, center of the body, plus radius of this sphere present at this corner. So we can see that this body diagonal is nothing but r plus 2r plus r. The diagonal means 2r. So r plus 2r plus r, that is 4r. Now also we have AD is equal to root 3a. We have obtained the body diagonal in terms of edge length also, and we have obtained body diagonal in terms of radius of sphere also. And since the body diagonal is one and the same, it means finally we can say root 3a is equal to 4r, or in short a is equal to 4r by root 3. So this time also we have generated a relation between the edge length small a and radius of these identical spheres small r. Now, like I said earlier, we have represented packing efficiency in short as P dot E, occupied volume of spheres in this unit cells as O dot C, and total volume of this unit cell as T dot V. So if I want to calculate packing efficiency, it is nothing but occupied volume, that is OV, upon total volume, that is TV, into 100. Occupied volume O dot V, occupied volume, T dot V, total volume, into 100. Now since this is body centered cubic unit cell, where you have atoms present at all the corners of this cube, and along with that you have one sphere present exactly at the center of the body. Now since the contribution from each corner of this cube is 1/8, as each sphere present at the corner of the cube is shared by 8 different cubes, 7 adjacent cubes to this particular cube. It means the part of that sphere present at the corner of this cube inside this cube will be 1/8. Since we have 8 different corners of this cube, that means if we join the shared part, the part of the sphere coming into this particular cube, if we join from all the corners, it will become 8 into 1/8, that is effectively 1. And also you have one sphere present exactly at the center of the body, so the effective number of spheres present in this cubic unit cell, in this body centered cubic unit cell, is nothing but 2. Now since occupied volume means volume of each sphere into number of spheres present in this cell, unit cell, so like I said, volume of a sphere is 4/3 pi r cube, as you have studied in lower standard also in mensuration. So the occupied volume becomes nothing but 2 into 4/3 pi r cube. 2 into 4/3 pi r cube divided by, since I have used small a to represent the edge length of this unit cell, and this unit cell is in the form of a cube where length is equal to breadth is equal to height, which means all the three lengths L, B and H are equal to A. So the volume of this cube becomes A into A into A, that is A cube. Now once again we have a problem that we have two different variables R and A in numerator and denominator, and we should have a relation between these two variables A and R, so that they cancel out and we are left with numbers only, so that we can calculate packing efficiency easily. And that is why we have done this previous part of work over here by calculating packing efficiency of BCC, and we have obtained the relation between A and R as A is equal to 4R by root 3. So if I substitute A is equal to 4R by root 3 over here, then it becomes 2 into 4 by pi r cube divided by cube of 4r by root 3 into 100. And if I open this bracket present in the denominator, it will become cube of 4 into cube of r divided by cube of root 3. Now cube of 4 is nothing but 4 into 4 into 4, that is 60 into 4, 64. And cube of r will be simply r cube, whereas cube of root 3 will be root 3 into root 3 into root 3, that is 3 root 3. Correct? So I can write it as 2 into 4 by 3 pi r cube divided by 64 r cube divided by 3 root 3 into 100. Now first of all, since we have r cube present in numerator also and in denominator also, this r cube gets cancelled. This 3 root 3 will go above, so or better you can cancel this 3 also present as a denominator of both numerator and denominator of this particular fraction, and you can take this root 3 above, so this becomes 8 root 3 pi upon 64 into 100. Now this 8 also, this 64 also get cancelled from 8 because 8 into 8 is 64. So this becomes simply root 3 by 8 pi into 100. Now if you substitute the value of pi as 3.14 over here, then packing efficiency turns out to be almost 68%. If you substitute the value of pi as 3.14 over here, the last expression which we have obtained from the calculation of packing efficiency, then its value turns out to be 68%. So let us just recall what we have seen over here, how to calculate the packing efficiency of body-centered cubic unit cell. Now first of all, do remember, in body-centered cubic unit cell, along with the corners, spheres present at the corners of this particular cube, there is a sphere present exactly at the center of the cube. Now from each corner, 1/8 of that sphere present at the corner, respective corner, is inside this cube. Since we have 8 different corners of this cube, the total number of effective spheres coming out from corners only is 8 into 1/8, that is 1. And above all, we have one full atom or sphere present at the center of this body. So effective number of spheres in this type of cubic unit cell, that is body-centered cubic unit cell, is 1 plus 1, 2. Correct? Now packing efficiency, like we have done earlier also in case of HCP and CCP, packing efficiency is nothing but occupied volume upon total volume into 100. Correct? Now occupied volume means what are the effective number of spheres coming inside this particular cube into volume of each sphere. Correct? Now we have 2 effective spheres inside this particular cubic unit cell, and volume of each sphere, like I said earlier also, we have studied in lower standards in mensuration also, volume of a sphere is 4/3 pi r cube, where r represents the radius of that sphere. So occupied volume becomes 2 into 4/3 pi r cube. Correct? Now since I have used small a to represent the edge length of this cube, and since all lengths and breadths and heights of this cube are equal in dimensions, equal in length, so the volume of this cube becomes a into a or a cube. So packing efficiency finally becomes 2 into 4/3 pi r cube divided by a cube into 100. Correct? Now since we have 2 different variables r and a in this expression, r present in numerator and a present in denominator, it is very important to have a relation between a and r so that we can cancel out these variables and we are left with numbers only. Because if we are left with numbers, then only we can calculate the precise value of packing efficiency in this particular case or in any other case. So in order to obtain that, we started with the relation to generate the relation between a and r only. So to eliminate that problem, what we have done is we have considered 2 different right angle triangles. Do remember, all the angles between any 2 edge lengths of this cube will be 90. Correct? In that case, if we take the top face of this cube A, B, C, D, E, F, G, H, if you take the top face, then there are 2 different triangles. I have considered triangle HGD, in which the angle HGD is 90 degree. Why? Like I said, angle between any 2 edge lengths is 90 in this cube. Correct? So angle HGD is 90. I have considered triangle HGD. I have applied Pythagoras Theorem, where HD represents the diagonal, that is the face diagonal. HD represents the diagonal of this triangle, right angle triangle HGD. And HG and GD are equal in length. Why? Because they represent the edge length of the cube. A and A, small a and small a. So applying Pythagoras theorem, I have calculated the length of HD in terms of a, small a, which is coming out to be a square plus a square, 2a square if I take the root of the equation. Then HD, the face diagonal length, becomes root 2a. The second right triangle I have considered is triangle AHD, where the angle AHD is 90. Why it is 90? Because they lie in two different perpendicular planes. AH is this length, HD is this length, correct? HD is this length and AH is this length. Since both the planes are perpendicular to each other, this angle is 90 degrees, correct? And AD is this length, which is one of the body diagonals which I have considered for the calculation, AD. Now since it is a right angle triangle, this body diagonal, which is also the hypotenuse of this particular right angle triangle AHD, applying Pythagoras theorem in this particular triangle, AD square is equal to AH square plus HD square, where HD is the face diagonal of the top face and AH is one of the edge lengths. AD is one of the body diagonal. So by substituting the value of AH and HD was turning out to be root 2a, AH is simply small a, that is edge length. So substituting these values and calculating, I have got the body diagonal as root 3a. Now since this body diagonal is just formed by the touching of three types of spheres, one present at the corner of the front face and the other present at the corner of the back face, top corner, and this one is the bottom corner, and there is exactly one atom present at the center of the body. Now since these three spheres are touching with each other, so this body diagonal is nothing but the radius of this left sphere plus the diameter of the middle sphere plus radius of the top sphere, which is r plus 2r plus r, that is 4r. Since the body diagonal AD in both the ways are one and the same, I can say that root 3a is equal to 4r or a is equal to 4r by root 3. Finally, I have substituted a as 4r by root 3 over here in the expression of time efficiency and have done the calculation and finally got the packing efficiency as 68%. Now let us talk about simple cube. Let's try to find the packing efficiency of simple cubic lattice, or also you can say primitive cubic unit cell, where the atoms or spheres are present only at the corners of the cell, cubic unit cell, correct? So let us draw the diagram for that first. Suppose this is our cube and the atoms are present only at the corners of this cube and these atoms are touching each other. Now for the sake of calculation I have drawn only two spheres, but you understand the atoms or the spheres are present at all the corners of the cube but only at the corners of the cube and no other position. That is what simple cubic or primitive cubic unit cell, if you remember, is actually. Now if I say let the edge length is represented by small a and the radius of each of these identical sphere is small r, then you can see that since if you talk about this particular edge length, then each of the corner is the center of corresponding sphere. It means directly we can say that a is equal to 2r. Why? Because this edge length has been formed by joining the two adjacent spheres, the centers of two adjacent spheres touching to each other. That means this edge length is simply r plus r or 2r. Now if we want to calculate the packing efficiency, as we have seen, packing efficiency is nothing but occupied volume of spheres inside this unit cell divided by total volume of this unit cell into 100, correct? So packing efficiency is occupied volume OV upon total volume PV into 100, correct? O dot V is occupied volume of spheres inside this unit cell, T dot V is total volume of this unit cell into 100. Now if you remember, since the spheres are present only at the corners of this unit cell and only 1/8 portion of each sphere lies inside this unit cell, inside this cube. It means if you join all those 1/8 portion of each sphere coming from each 8 corners, then it will result into one effective sphere. How? 1/8 plus 1/8 plus 1/8, 8 times. It means 8 into 1/8. 8 get cancelled, and then effective number of spheres by joining those parts becomes 1. So it means this type of unit cell, simple cubic lattice or primitive cubic unit cell, basically consists one effective sphere, and the occupied volume will now become simply 1 into volume of a sphere, that is 4/3 pi r cube, as we have seen in earlier cases also. Correct? So the numerator here becomes simply 1 into 4/3 pi r cube divided by the volume of this cube. Once again, since it is a cube, the volume of this cube becomes cube of small a into a into a, where small a represents the edge length of the cube. So this divided by a cube into 100. Now, like every time, we should have a relation between small a and small r, where small a represents the edge length of the cube and r represents the radius of these identical sphere. Here we simply have a is equal to 2r. Why? Because this cube has been obtained by joining the centers of 8 touching spheres. This cube has been obtained by joining the centers of 8 touching spheres. It means if I take one of its edge length small a, then it is effectively the sum of 2 radius of 2 adjacent spheres. Or in short, small a is equal to r plus r, a is equal to 2r. Now if I substitute a is equal to 2r over here, then it becomes 4/3 pi r cube upon cube of 2r into 100. Correct? If I expand the denominator, it becomes 4/3 pi r cube divided by cube of 2 is 8 and cube of r is simply r cube into 100. Now finally we have same variables in numerator and denominator also, r cube in numerator and r cube in denominator also. We can cancel out r cube and r cube, so we are finally left with numbers. Now this 4 into 2 is 8, so it becomes pi by 6 into 100. If I substitute the value of pi, that is 3.14 divided by 6 into 100, and if I calculate these numbers, 3.14 divided by 6 into 100, then this packing efficiency turns out to be 52.36%, or we can say packing efficiency is roughly 52.4% if we round off this number. So packing efficiency of this third type of unit cell is coming out to be 52.4%. So let me just quickly recall you how we have calculated the packing efficiency of this type of cubic unit cell, that is simple cubic unit cell or simple cubic lattice rather, also called as primitive cubic unit cell. Why? Because the spheres or atoms are present only at the corners of this cube and no other position. Correct? Now since all the spheres are touching to each other, so if you join any two adjacent sphere, then the edge length A will simply be the sum of radius of both spheres. That is, and since the spheres are identical, so A is nothing but r plus r, that is 2r. Now like every time, packing efficiency is occupied volume of spheres in this unit cell divided by total volume of this unit cell into 100. Now effectively this unit cell contains only one atom. Why? Because the contribution, the part coming inside this unit cell from each sphere, from each corner, is simply 1/8, because each sphere is shared by 8 different unit cells. So equal portion for each cube will be simply 1/8. Now since there are 8 different corners in this cube, so 1/8 coming from each corner means 8 into 1/8, that is 1 effective sphere will be there if we join all those parts. Now occupied volume, since the volume of a sphere is 4 by 3 pi r cube, where small r represents the radius of that sphere and effective number of sphere is coming out to be 1. So this occupied volume, the numerator simply becomes 1 into 4 by 3 pi r cube, which means simply 4 by 3 pi r cube. The total volume, that is the denominator, is the cube of this unit cell, that is the cube of the edge length of this unit cell, that is a cube. And since again, like every time, we have two different variables, one in numerator, one in denominator, that is r and a respectively, we need to have a relation between a and r, so that we are left with only numbers and we can calculate time efficiency easily. That is why we have a is equal to 2r. If I substitute a is equal to 2r over here in the denominator and expand the denominator, then cube of 2r will become cube of 2, that is 8, and cube of r, that is simply r cube. So we have r cube in the numerator also, we have r cube in the denominator also, which gets cancelled out and we are left with the numbers. From doing the calculation, the packing efficiency is turning out to be 52.36%, or if you round off the number, then it becomes 52.4%.